Okay, I'm assuming that if you're hearing me now, you've looked at the plant, or you and have some answers, or you looked at the plant and you're feeling a little frustrated, and decided just to see what you could learn by, you know, hearing how I would go about doing this. And I want to emphasize, I'm showing you things I do, like, and these are, based on my experience, and I, I've been doing this for a little over 40 years, so I do have some experience. But by no means are these answers the only answers or the only way to do this. I'm just going to show you some stuff that worked for me. Another thing to remember about this is, most of the time when we're out in the field like this, especially at this point in a project, this is not an exact science. Okay, so these things we're concluding, or these conclusions I'm about to postulate, are ifish. Okay, they're approximate. In fact, a lot of times I never give anybody an exact number. I give them a range of numbers, because even after you've done the math, there's so many variables in a building and its systems that you aren't the answer isn't like 1200.97652 tons. The answer is it's about 1200 tons. Okay, so having said that, let's go ahead and open up the plant model and start taking a look. And from this perspective, you're actually in sort of a good position to answer my first question, maybe. And that question was, do you think it's a constant volume plant or a variable flow plant? And if it's variable flow, do you think it's variable flow primary only? Or do you think it's variable flow primary secondary? And so a real easy way to sort of get a feel for that would be to just look at how the chillers are piped and how many pumps are there. If this was a constant flow plant, there's a pretty good chance there'd only be one pump for each chiller, or certainly there wouldn't be two piping loops. And you can see from this perspective that there are two pairs of pumps. And if you start looking at what the pipes from the pumps do, for instance, this pump, the pipe drops down, goes into the pump, it goes out, runs through the chiller, comes out of the chiller, comes back, picks up the other chiller, comes back to a T in the pipe, and then the T in the pipe goes to the other pair of pumps, and also to a pipe that actually reconnects to the suction side of the pump we're thinking about. That's basically the distinguishing characteristic of a variable flow primary secondary system. In other words, there's a pump dedicated to the chillers, or sometimes the pumps are in a header and the header is dedicated to the chillers, and then there's a totally separate set of pumps on a totally independent loop that distribute water from the water to the loads, which, at this point it's a reasonable assumption that the pipes leaving the plant, the big pipes leaving the plant, are the pipes to the loads. And so that information sort of points you in the direction of this being a variable flow primary secondary plant. To be absolutely sure it was variable flow, you'd want to look at some of the loads. In other words, you'd expect the loads in a variable flow plant to have two-way valves on them. There'd be an occasional three-way valve, probably at the end of the mains, to keep flow up, and which guarantees a fairly consistent response characteristic, and also keeps the water quality better because flow is constantly running out to the end of the system and back. But by far and large, a plant that's intended to operate as variable flow, most of the loads ought to have two-way valves on them. So you might make a mental note, hey, when I get out to one of the air handling equipment rooms, I'm going to take a look at some of the control valves and see if in fact they're two-way valves. The plant certainly looks like it's set up to leverage that, and that's an energy conserving thing, right? If you vary the flow, remember that equation, the flow's in the numerator. If you reduce the flow, you'll reduce the energy requirement, partly because you reduce the flow, but also because the pressure drop in the piping is a function of the square of the flow. And so there's actually a cubic relationship for a fixed condition between the flow in a system and the power required to produce that flow. So it's a very powerful relationship. And it's not out of the question that you'll go into a plant that's supposed to be variable flow, it's configured as variable flow, but it actually isn't running that way because for whatever reason there's three-way valves out in the system, a lot of three-way valves. I've seen it before, and so that'd be an opportunity. So answer the first question is that it's a variable flow primary secondary plant. If it was variable flow primary only, the pumps that pump the chiller would also be the pumps that are pumping the loop. So variable flow primary only at the plant might look like a constant flow plant. So you'd have to go out and look at the loads to be sure. The other thing you'd see in a variable flow primary only plant, probably in the plant, there'd be a bypass line like this from the supply header to the return header, but there'd be a control valve in it, and it would be after the pumps. There'd be a control valve in it because even in a variable flow primary only plant, you can't let the flow to the chillers drop below a minimum safe level. So there has to be a mechanism in place to keep minimum flow up to the plant. That's not always in the central plant. Sometimes it's out of the end of the system. There's different design philosophies about that. But that'd be another clue. Okay. So the second question I ask is, do you think the chillers are redundant chillers, or do you think they're both required to peak? And there's a couple of ways you could reach the conclusion that I'm about to reach. Maybe I'll just give you the answer first. In this plant, both of these chillers are actually designed required to peak. There's a couple ways you can reach that conclusion. One way would be to talk to the operators, of course, but they aren't there, right? They're not down there right now yet. And so another way would be to start taking a closer look at the chillers. And if you really look closely at these chillers, initially they appear identical, but they actually aren't identical. And I'm going to do something actually in more depth with that later on, but the chillers are not identical, and some of you may have noticed that, some of you may not have noticed that, and we'll get into that in one of the modules that's going to come up after this, because we're going to go look at that in a lot more detail and why that matters. But the chillers aren't identical, and so what that implies is if the chillers aren't identical, there's probably a reason they're different. There's probably one chiller that's intended to carry the load swings and low load conditions, and another chiller that's intended to be a peaking machine. So that would suggest that both chillers are intended to be in operation when the plant is at full load, versus one chiller is a redundant chiller for the other chiller. Another thing you could look at is if you had the control drawings, or if you'd been successful in procuring those before you came on site, the sequence of operation may tell you, that when the plant peaks, both chillers have to run. A lot of times when you get to the site for the first time, even though you've asked for this information like drawings and control drawings, they may not have gotten the copies for you yet, and so you may not have that resource there, but they may be available down in the chief engineer's office or the director of engineering's office or in their files. So that might be another way you could go look in their files. A third way would be just to take a look. I'm going to go back to the original view. Take a look at the size of the pipe leaving the plant. And here's a place where our ruler would come in handy. If you measure this pipe, now we can measure the cross section because this pipe isn't actually full of water and we have it cut. Out in the field, what you'd actually do is measure the circumference of the pipe, measure the thickness of the insulation somehow, and then calculate the diameter of the pipe based on the circumference compensated by the thickness of the insulation. Here we can just actually easily, I think my system's paused a minute, it's doing an automatic backup here. We can actually take our ruler tool when this little automatic backup quits. We can take our ruler and we can basically measure the I forgot that the system would do this. I have it's doing an automatic backup every 15 minutes because when I'm designing, you sort of hate to lose a bunch of work because you forgot to back up. I'm just getting rid of the guides that accidentally got put in there. Okay, so we can measure the radius of this pipe, and the radius of the pipe is 6 inches, so that's a 12-inch pipe. Now, if you're doing this a lot, you might already know that, well, a 12-inch pipe is good for quite a bit of flow. And if you go look at the nameplate on these distribution pumps, remember I mentioned that there's a lot of detail available. You discover that these pumps are identical. We could look at them both, but I'm just going to tell you that. They're identical, and each pump's rated for 1100 GPM. So the question then becomes, is the pipe leaving the plant an 1100 GPM pipe or a 2200 GPM pipe, or how much capacity does the pipe leaving the plant have? If it only has 1100 GPM capacity, there's a pretty good chance that the plant isn't intended to have both machines running simultaneously. If it has 2200 GPM of capacity or so, probably means, yeah, the plant was designed for both chillers to run concurrently. And if it has even more capacity than that, it probably means the plant is actually intended to have additional capacity added to it at some point. Another clue in that regard would be if you go back here and just look at the piping a little closer, you discover there's some capped T's in the piping, both here and where the chillers are. That kind of implies they have provisions there to add pumps and add chillers. So how do you figure out what the capacity of a pipe is? Well, you can use a pipe friction chart. And I have a little tool I made. If you were to go out to my website and go to resources and go to tools, you'll discover there's a pipe friction chart tool there. And rather than download it and open, I'm just going to open a local copy. So here's the local copy. And basically what you do is you start out by putting in the flow rate you're interested in. So I'm going to, and the instructions tell you this, so I'm going to put in 2200 GPM because that's the total for the two distribution pumps, okay? And then you click onto the friction chart tab, and basically what you just did was set this red vertical line, okay? Designers will pick a pipe in our industry so that the friction rate is typically 4 feet per 100 or less. Now you can be more sophisticated about that. You can actually do a life cycle cost based sizing operation, and in process they actually might go for higher friction rates because you aren't so worried about noise, and you may figure, well, I'm going to replace this pipe when my process changes, and so they're not as worried about erosion. But in our industry, we're tending to think, we'd like this pipe, this building could be around for a really long time. We'd like the pipe to last, so I don't want to erode it by having the velocity too high, and I certainly don't want noise. I don't want to bother people with the sound of water flowing in my pipe. And it turns out that 4 feet per 100, which is this dotted blue line, is a friction rate that'll keep you out of trouble. And so what that means is you need a pipe that these slanted colored lines are different line sizes, okay? So you need to pick a pipe where the dotted red line crosses the slanted pipe size line at or below 4 feet per 100. Well, you can see an 8-inch pipe would be over 4 feet per 100. It'd be up, 5, 6, 7 or so feet per 100. So 8-inch would be way small for 2200 GPM. The next size up, 10-inch, has a friction rate down around 2 1/4, 2 1/3 feet per 100. So if this was a 2200 GPM plant, you'd expect at least a 10-inch pipe. We discovered it has a 12-inch pipe, which is a really low friction rate for 2200 GPM. So that basically is a strong indicator that the plant is definitely a plant that's intended to have both machines running at the same time, and may even be a plant where they intend to add capacity at some point. Okay, so those are the field clues you could use to sort of understand, what the peak capacity on this plant might be intended to be, and if the chillers are supposed to run together or not. Okay. Now the other question I ask you is, what do you think the capacity on the chillers is right now? In other words, what's the tonnage on these chillers right now? There's a couple ways that you could do that. You could basically, the first thing would be to say, well, how many of them are running? Are any of them running, in fact? And so, like, I clicked the wrong scene there. If we come over and take a look at this chiller, we'll discover it's off. Okay, it's ready to run, but it's off. And in fact, if we go over, oops, went too far. If we go over and look at its starter, we discover there's no volts, no amps. The starter is disengaged. Okay, so that machine isn't running. And if you're there in the field, it wouldn't be making noise either. That'd be kind of another clue. If we go look at the second machine, use the same technique. It says it's running, it's in auto, it's using 188 kW. Okay, and if we looked at its starter, we discover, well, yeah, there's 480 volts on it, and it's up in the 200, 300, 260 or so amps on it. So yeah, it's definitely using some power. And so then the question becomes, well, how close to full load do we think that is? And so 188 kW, one thing you could do is you could say, well, in round numbers, just based on my experience in this industry, fairly current technology machine might be at a half a kW per ton machine or better. Okay, so if this was a half a kW per ton machine, 188 kW in round numbers would be about twice that many tons. So 188 times 2 would be 200, 2 times 8, 360 tons. Now, it's probably not that heavily loaded, because at part load, if you know about chiller performance curves, there's actually a sweet spot that's at a part load condition. So the half kW per ton, full load kW per tonnage is probably high for the part load condition. But one thing you could conclude is, well, this machine's probably got, certainly got a load on it. Probably not 300 tons, but it's got a load on it, right? And in terms of full capacity, how much is this machine rated for? Well, you could use the pump nameplate information, and you might find a nameplate on the chiller, but interestingly enough, most chillers don't actually have the rated tonnage on them, not on a nameplate. You have to get into the submittals for that. But a field clue would be the flow rate through the evaporator and the flow rate through the condenser. And so, for instance, we know the pump in this evaporator is an 1100 GPM pump. And if you do the math, at 1100 GPM, a machine that's 2 GPM per ton has a 12 degree delta T across it. So 12 degree delta T is a real common design metric for plants. I mean, they can be as low as 8 or even lower. And I actually was in a plant recently that was actually designed for a 20 degree delta T, which is actually really hard to make happen. But it's real common to see plants picked at 10, 12, 14 degree delta T's. And so if you just keep in your head 2 GPM per ton, 12 degree delta T, you can sort of ballpark the machine's capacity off the evaporator pump flow rate. And so if we go back and look at that evaporator pump again, oops, went a little too far there. If we go back and look at the evaporator pump, 1100 GPM at 2 GPM a ton would basically mean that that's about a 550 ton machine. Okay, so we have a plant that's probably in the range of 1100, 1200 tons of capacity that right now might be running with one machine 50% loaded or not. Okay, and so at that point, I think I'm going to stop this bite right here, because we're getting up into the 23, 24, 25 minute range. Let you absorb that, and in the next module, we're going to ask ourselves an important question. And that question is going to be, should there be that kind of load on this plant? Okay. So, thanks for taking the time to hang out with me for a little bit. Hope you're starting to enjoy this now that we're actually doing something meaningful. And take some time to absorb it. Maybe go back and review the scoping. See if you can, now if you didn't reach these conclusions on your own, now that I've sort of guided you through it, sort of backtrack it. Try walking through and see if you can mimic what I just did, and that'll help reinforce those concepts. When you feel ready, open up the next module and we'll ask and answer that question. Okay, thanks much.